Hey scholars, it's good to be back with you. Today I'd like to talk to you a little bit about finding roots of equations. Now, I'm going to tell you a little bit about how to do this using a numerical process called bisection. But before we go into that, let's talk about why you'd actually want to do this. Now, we learn about finding roots of equations, most of us in junior high school, I imagine. And it's a very basic process, but it seems really abstract. It seems very disconnected from our daily lives. Why would I want to do this? There's two parts to the puzzle. The first part is that mathematics describes the world around us. When we write equations on a piece of paper, most of the time, those equations mean something important to us. It may be describing some physical process. It may be describing some human process, like how a factory runs or something. It may be describing money. It may be describing all kinds of things. But we use mathematical equations to describe things we want to know about. So that's part one of the puzzle. Part two of the puzzle is no matter what equations you write and no matter what they mean, eventually you can put them in the form of f of x equals something, and more specifically f of x equals 0. Almost all equations can eventually be written out as some function equals 0. Okay? An equation is just two expressions separated by an equal sign. Whatever's on one side of the equation equals whatever's on the other side. So it's easy to take one side of the equation, subtract that from both sides, and you get something, new function, equals 0. So no matter what equations you write, eventually you can write them out as something equals 0. Okay, now we're in business. Once you have something equals 0, solving that equation means finding a root. Okay, equation means something important, and you can always write it as f of x equals 0. Those are the two parts of the puzzle. Those are why you'd want to do this. So let's talk about how to do this. Well, when we talk a lot about polynomials, partly because they're pretty handy and partly because they're easy to solve. Now, this is a cubic polynomial. It's got a power of 3 in it, and it's one step up from a quadratic equation. Now, you may remember from, again, junior high school probably, that there is a quadratic formula. If you take the coefficients of the equation and you ram them through the quadratic formula, you get the answer. You get the roots of the equation. There is a cubic formula. It's about that long. There's actually a quartic formula. It's about that long. There is no formula for any equation of a higher order than that. But most of that doesn't matter. In practice, very seldom does anybody ever solve these things analytically. And analytically, I mean pushing symbols around on a piece of paper until you get x equals something. In practice, that's very rare anymore. You see it sometimes in derivations of things, but very, very seldom does anybody in practice ever sit around and write out analytical solutions. It's almost always numerical. Almost always we have a computer do it for us, or your calculator or whatever, but you type the equation into some piece of software, punch a button, and out comes the answer. That's what we almost always do anymore. So what I want to do is we'll use this as an example, and I'm going to show you, here it is graphically, and then we're going to use something called the bisection method to solve it numerically. So what does this equation mean? Well, I just made this up. As far as I know, it doesn't mean anything. And it's only got one real root. If you run this through your favorite equation solver, you'll find out it's got one real root right there, 4.361, and it's got two imaginary roots. Well, the reason I picked this is that there's only one real root. It's a pretty good example to use for bisection. So here's the equation. You run it through the solver. There's what you get. And when you draw a picture, here's what it looks like, pretty much. Now I've drawn this on my board freehand, but it's pretty close. So let's see, let's grab green right there. Right there. That's a root. That's where this equation equals 0. When you solve f of x equals 0, you're saying find the value of x that makes this equation equal 0. Well, there it is. That value of x is 4.361, pretty much. There's more decimals out there. And it shows where my function goes through the x-axis. It shows where the function equals 0. So root means where that goes through 0. Easy. Now, why don't we just plot it out every time? You know, your calculator has that little plot function on it. You can plot it out. Why don't we just do that every time? Why bother with an algorithm to find this efficiently? Well, the problem is sometimes this isn't just one equation. Sometimes it's more than one. And also, sometimes this equation is pretty hard to evaluate. So just simply plotting the equation out and finding the root isn't always practical. That's why we have root finding algorithms. The simplest of these methods is called the bisection method. It also gets called binary search. Okay? It's got some other names as well, but those are the two you see most often. And it's really straightforward. Here's how it works. And let's see, let's grab a blue pen, I guess. Every root finding algorithm needs a starting point. Well, in binary search, you need two starting points. You need a lower and an upper. And what you're assuming is the root lies somewhere between your lower and your upper. So let's start with lower one, and I'll call that x0 equals 0. I'll just start there. And right here, I'll say x1 equals 6. Okay? I know that the root lies in there somewhere. Well, how do I know? Well, I plotted it out. It's kind of cheating. But if you don't know where the root is, you just set the limits so far apart, it's got to be in there somewhere. Right? So what I'm going to do is I'm going to divide this in half. That's the bisection method. Right? So if 0 and 6 are my endpoints, I'll divide it in half. Well, what's between 0 and 6? 3. Okay, let's see. This is an... and I'll just write that. I'll call that bisection. That's the halfway point. Now, this isn't exactly halfway. If you get your calipers out, you find out that when I drew this on the board, I didn't get the scale quite right. But you'll get the idea. And so I bisect it. All right, I'll look there. Now, I go, is the root there? Or is the root here? Well, it's not there. It's here. Okay. And let's see, here's my eraser. Okay, so now I say x0 equals 3. I don't need that anymore. All right, divide it again. That's the bisection. Divide it again. Well, is the root here or is it here? Well, it's over here. Okay, so that becomes my new lower limit. And you go, and you go, and you go. So the game we're playing here is we're trying to find the root in as few function evaluations as we can, because sometimes the function evaluations are expensive. So we're trying to find a root doing as little number crunching as we possibly can. Well, how do you make a plot? You grind out this function a whole bunch of times and you draw lines between all the points. Okay, this is what we used to call hitting the problem with a very big hammer, to just plot that out. We don't want to do that. We're trying to find the root in as little calculation as possible, and bisection is one way to do it. So there's how it works. Let me write down some numbers for you. Oh, look. The whiteboard elf came and took care of it for me. So anyway, here we go. Here's how you do this. We're going to expand this out, and we're going to use an iterative process where we go through the same process over and over and over again. And as we do it, our estimate of the root is going to get closer and closer. So here's the first iteration, iteration number 1. I said x0 equals 0, x1 equals 6. Okay. The bisection, I'm going to call that delta x. That's the distance from either end to the middle. That's 3. 6 minus 0 divided by 2 is 3. So that's halfway in the middle. And this isn't quite as obvious now. F of x0, that's the function evaluation at one end of my range. F of x0 plus delta x, that's the function evaluation in the middle. And f of x1, that's the function evaluation at the other end. I don't care what these numbers are. I only care if they're positive or negative. If it's positive, it means either both of these were positive or both of them were negative. But what it means is, if this is positive, the root didn't lie in between those two endpoints, the endpoint and the middle point. Here, it does lie between the middle and my upper bound. So somewhere between 3 and 6, it went from positive to negative. And it doesn't matter which way I go. If I go from negative to positive or positive to negative, I still get a negative number there. So what this means is the root lies in this range somewhere between x0 plus delta x, and x1. All right. Now I know it's not here. I don't have to look there anymore. It does lie there. So let's see, for iteration 2, all right, x1 is now 3. This is 6. Delta x looks like it's going to be 1.5. All right, now I'm going to go to my cheat sheet here, and I'm going to write these numbers down real quick. Just give me a second. All right, so there we go. Negative number. Okay, that means the function went from negative to positive, or positive to negative, whichever, in this range from 0 to 0 plus delta x. All right, so I know now, I know it's in this range. I know not to worry about that. So iteration 3, let's just keep going. I'll keep this. This is now 4 point, whoops, messed that up, didn't I? That's now 4.5. And this is now going to be, let's see, 0.75. It's half of that. Notice how these keep going down by half every time? The nice part about this is this number gets smaller and smaller and smaller. The range in which the root lies keeps getting smaller and smaller. So not only am I converging on the root as I go through more of these steps, I know how far apart my range is, so I have a very good estimate of what my error is. And this process is really easy to execute, so I can just keep going through this loop as many times as I want. I can go through this as, I can go as many decimal places out as I care to. Now, rather than drag you through all of it, give me a minute, and I'm just going to write down, I think it's iteration 7 here. I'll give you a pretty close estimate. And remember, we know what the answer is. I already ran this through the root finding algorithm in MathCAD, so I already know what the right answer is. Now, does it make sense here? Does the root live between 3 and 4.5? You bet it does. Now, this is already pretty close. That's pretty far away. It wouldn't surprise me at all if the next iteration said the root was closer to this one, and so x0 changed. That might happen. But I'm going to skip ahead a couple, and let me write down iteration 7 for you. Okay, so here we go. Skipped a bunch of steps, and I'm now at x0 is 4.359. Well, is that pretty close to that? That's really close to that. 4.406, also really close to that. Look how tiny that delta x is now, right? Very small. F of x0 times f of x0 plus delta x, small number, positive. So it means the root does not lie in that range. It means it does lie in this range, because that number's negative. Let me get my teapot out of your way here, and my ping pong ball. Okay. Does lie in this range. So I can actually cut this down one more time if I want to. But look at how these numbers started out. The magnitude's really big, and they kept getting smaller and smaller as you go down. Well, as you get closer and closer to f of x equals 0, this number better get pretty small, and it does. So here we go. This is the bisection algorithm, or the binary search, whichever you want to call it. Gone through 7 steps here, got a pretty good estimate of that number, and I can keep going. Now, before I let you go here, is this the most efficient root finding algorithm out there? Absolutely not, but it is the simplest. Other methods work more efficiently, and other methods will get you a good answer in fewer iterations, and that means fewer calculations, fewer function evaluations. But it's just a matter of degree at this point. They all work kind of like this, or alike enough, and there are ways you could make this more efficient, but that's for another video. So let's review real quick. Root finding, real important for 2 reasons. 1, equations tell us something important about the world around us, and no matter what equation you write, you can eventually write it out as f of x equals 0. Kind of like that. When you find find a value of x that makes the function equal 0, that's root finding. So root finding is really, really important for practical problems. There are lots of practical reasons why you'd want to do this. You learn in school how to do this analytically. In practice, nobody does analytical root finding anymore. It's all numerical. So then we used the bisection algorithm to find lay out a very simple method for finding roots using number crunching, used numerically. And here it is. We got a pretty good estimate, and we know that we can just keep this going as long as we want. We can make it as precise as we like. So there you are. I hope this helps, and we'll talk to you next time.